So which of the following is the graph of the parametric curve? So we have a coordinate pair here, right? So when we read this here, we're thinking, oh, this is our x coordinate, and this is our y coordinate. And so x and y are functions of t. They move according to how t moves. And we're told that time goes from negative pi over 4 to positive pi over 4. And we have 5 graphs. We just have to say, well, which one is the right picture? All right, A, B, C, D, or E. What's the answer? A? Good choice. Not quite A, but you're in the ballpark. B. B is the answer. All right. So, how do you identify? Now, there's a couple things you can do, and there's some suggestions here that are useful. One suggestion, and this often happens, in fact, it happens for the problem we finished up last time. We'll come back and revisit that in a few minutes. If you're struggling with the whole picture, just look at a part. Just look at what happens with x or what happens with y. So one thing is, if you look at, say, the y value here, 2 minus tangent of t, you can take its derivative and see it's negative, which means it's always going downhill. Now you might say, okay, well, does that rule anything out? No, not really, turns out. But you might say, well, wait, isn't this going uphill? But is it? That's the thing, you don't know. Part of the challenge is we don't know what the orientation is. Because we don't just have a curve, we also have a way we travel on the curve. So there's sort of a natural orientation here for the t inputs, but it doesn't mean we have to follow that same for the outputs. So what can you do? Well, there's another piece of advice. Check some points, and particularly endpoints can be helpful. So what do we mean by endpoints? Well, look what happens at the extreme cases. So you can plug in negative pi over 4. And if you plug that in, you get the point 0.03. And if you plug in positive pi over 4, you get the point 4.1. So we should start at 0.3, we should end at 4.1, and we should be going downhill. So what satisfies all of those? And the answer is B. And you can check, we do match the include, the start at 0.3, and then we go downhill to 4.1, and that's pi over 4. All right, good. Well, any questions on that one? Okay. Well, our thought for the day. And this is a movie quote from Planet of the Apes. Now, I know this line was delivered by sign language, but I'll still try to emulate sort of if it were spoken in the movie. It goes something like, ape alone, weak. Apes together, strong. All right, so what's the idea here? You know, you should work together. I think that math is learned best by talking and sharing ideas. And one of the things that often happens is that it's very difficult to catch your own mistakes. I don't know if you've ever had this experience when you know you've made a mistake but you can't find it. But it's relatively easy to catch somebody else's mistake. You'd be like, aha, I know where you went wrong. So one thing you can do is work together and say, look, we'll take turns and we'll compare notes. And by doing that, you both get better. And so I strongly encourage you, don't succumb to this false belief that mathematicians should be sort of introverts that stay inside their dorm rooms and write on the windows. No, that's not how math gets done. Math gets done and math gets learned by working together. The more you work together, the better you'll get at doing math. All right. Well, what are our goals for today? We need to finish our introduction to parameterized curves. We didn't finish it last time. We're going to start applications with parameterized curves. really the big thing is we're going to talk about length and how length comes in. And then we'll say, well, there's sort of two different types of applications that can be looked at. One is applications which use length. And so, for example, surface area or mass of wires, things of that nature. And we'll see that those are really quick to adapt, super simple. And one is applications that don't use length, things like area and volume. And those are also relatively quick to adapt, but you have to be a little bit careful. I suspect that these parts we will get to next time, and I'm hopeful to get to these parts today. Now you might say, all right, are we learning anything new from our formula sheet? Sort of, yes. The big thing is we have a new formula for length, and these parts that I've marked here are examples where we can see applications of parameterized curves to ideas that we've already discussed before. But of course, the big formula in terms of the formula sheet is length for our parameterized curves. Okay. Well, before we go on, a quick callback to the end of last time. Because we finished this pretty quickly. I think there might be some skeptics in the audience as to some of these answers. So I want to talk about some of these answers. Is there anything among these 5 that you're skeptical about? You'd be like, hold on, explain to me why this worked. Answer B. E. Answer E. Well, that's not too bad. Sure, we can do that one. I know which one you meant. Okay, all right. Now, this one, E. So there's a couple of things that we know how people think, and it's psychological. And so this was written in a way to sort of give you hints of things that you might be misled on. You say, -1 to 1, and I look like I have 1 minus something squared. And you're like, oh, this looks like 1 minus x squared from -1 to 1. So you're naturally inclined to say, that's what I must be going for. But you have to remember that these values that you have for t are not your x values, they're not your y values, they're your parameter. So they don't directly map to x, they don't directly map to y. So you have to think about what do they do. Now, what's another name for 1 minus cosine squared? Sine squared. So you have sine, comma, sine squared. So it's like, oh, this falls into the same thing, like something, something squared, something, something squared. In fact, all of these fall into the something, something squared. But of course, we use trig identities to hide that fact. So, okay, so it is something, something squared. Now, you might say, but wait, you have open endpoints on both parts. So shouldn't there be open dots on both ends? None of these pictures have that for x squared. So let's talk about what's happening to sine pi t. And so we'll do a quick little sketch here. So this is not the xy plane. Here is t, and I'll put x here. So we're going to graph sine pi t. Well, what does sine t look like? Do we know that? Up and down. What does sine pi t do? Compresses. So what's going to happen is if you look at the graph, you're going to have something that looks like this. And I'm going to have open endpoints here. And we'll get to y in a second. Because we're only going from -1 to 1, but not including the endpoint. So that's what your sine of pi t is doing. All right. So think about where are you. When you start at time -1, now technically speaking, we don't actually start there. But at time -1, what's your x value? If we did include it. At -1, what's the x value? 0. So it says you should be starting here, and then what happens to your x value? You get more negative. So you go up, Then you go back down. Then your x value goes up. Then your x value goes back down. So this curve here is going back and forth along the curve. And so the reason why we include these endpoints is these aren't the ends of time. They actually occur at different locations in time. So going back and forth. So parametric curves can trace over themselves. And this can sometimes lead to confusion and obfuscation. You just have to recognize that it can happen. So just think about what's happening with your coordinates. And it turns out that to answer these problems, the only thing you have to check is say, which x values do I hit? Because each one of these pictures, you hit a different range of x values. So if you say, look, I'm not even going to look at the y values, I just have to look at the x values, that's enough for you to determine which one is the right answer. All right. On a side note, this fourth option is another one that might lead you to say, oh, I see I include 0 but not 1. It might lead you to think, the correct answer is here. I'm including 0 but not 1. But the problem is, what's happening to your x value? Where do you start? At time 0, you're starting where? 1. And you're going to time 1, which is heading to 0. So you're actually running that direction. So you're running down the curve. So again, be careful. There's a lot of hidden assumptions that we make because we're so used to y equals f of x that we have to be careful and say, hold on, we aren't in y equals f of x. We're in parameterized curves. We're not going to fall for that trick. All right. Well, let's try another one. Now, the unit circle, very commonly used circle. Now, what does unit here refer to? When you hear unit circle, what does that mean? Circle has radius 1. Just think about words that start with una. You know, you have like unicycle, something with one wheel. Unibrow, only one eyebrow. Unicorn, only one corn. All of these indicate oneness. So unit circle means there's something about 1. So unit circle means radius 1. So if you have a unit circle centered at the origin, then there's this really clean parameterization. And that is to say that the x values are cosine and the y values are sine. And that's essentially how trigonometry is done. There's two ways to approach trigonometry. And one way is to approach it by saying, I'll think of triangles. The other way is to think of it in terms of a circle. And the way we usually mark this is we say, here, at this point, this is cosine t, sine t, where t can be measured as an angle. Now, I haven't given a range of values. You can assign range, just depending upon how much of the circle you want. You can even wrap around the circle multiple times if you want. All right, so if you ever have to deal with a circle, be ready to think cosine and sine. All right, so here are some questions. For the unit circle centered at the origin, give the following parameterizations. All right, option A, go twice around counterclockwise from 0, 1 to 0, 1. Where is the point 0, 1? That's the top. So it's telling us we need to circle around once, twice, and stop. All right. Well, what can we do? Any suggestions? Do we have a parameterization of the circle? Anywhere. Any parameterization at all? Anything?
Do we put the numbers into the cosine t and sine t?
So we have a parameterization, right? Cosine t, sine t. So we say, great. Now, what do we need to do? We need to adapt it. We need to be adaptable. Now, cosine t, sine t does go counterclockwise. That's great. So what do we need? Well, we just need to make sure we start at the right place. We need to make sure we go twice around, and that way stop at the right place. So here we can say, all right, let's just take our standard parameterization. Life is good, but we need to decide where to start and stop. So where do we start? Where do we stop?
Start at pi over 2.
Okay, so we can start at pi over 2. Where do we stop? Pi over 2 plus 2 pi? Will that be enough?
4.
Pi over 2 plus 4 pi? Will that be enough? Yeah, 4 pi is correct.
Okay.
Right? Because 2 pi takes you all the way around once. So, what's pi over 2 plus 4 pi? 9 pi over 2. All right, so this is our pi over 2 plus 2 times going all the way around. Now, is this the only way that we could have done it? Is this like, and that's it. There's no other possible way that we could have written this parameterization. How about the following? You can tell me whether or not it works. Let's do cosine pi over 2 plus 4 pi t sine pi over 2 plus 4 pi t, and where t goes from 0 to 1. Will that work? Yes, it will work. Okay, so these are not unique. Parameterizations are not unique. So you have to be open to, there might be multiple correct ways to write the parameterization. Now you might say, well, which one's the right one to use? The answer is whichever one's convenient. So try to find convenient parameterizations. All right. Well, with that one out of the way, option B, go clockwise on the top from negative 1, 0 to 1, 0. So to redraw, what are we doing? We want to go from negative 1, 0 to 1, 0. So that's what we're trying to do. We're going on the top half. But we're going clockwise. Can we do it? Do we have the technology? So there's a lot of options. Somebody was giving a suggestion up front that says, what if you just do the following? Cosine pi minus t, comma, sine pi minus t. Where would t go from? 0 up to pi. Would this work? So what is the pi minus t really doing? In essence, it's running your t backwards. If you think about what the 4 pi t was doing up here, it was speeding it up. It was, hey, t should run faster. So that's why we were able to do it in an interval from 0 to 1. The minus in front says, oh, you should run backwards. Now, is this the only way to do it?
will say no.
Okay, someone would say no. Anyone have a different way they'd like to suggest? We don't have to write down another one, but no. All right, I guess nobody has a different way. But there are other ways to write these down. So let's see, maybe we should try one. What if I said sine t, cosine t, and have to think about this one for a second here. And I want to have, I should not have tried this in real time. Okay. So negative pi halves less than or equal to t, less than or equal to pi halves. Would that work? Yes? No? Yes. Think about what happens at negative pi halves. Sine of negative pi halves? Negative 1 cosine negative pi halves? 0. And now imagine we move forward. Let's suppose we're at time t equals 0. Plug in time 0. Where are you at? 0, comma 1. So you've moved to there. Go to pi halves. What do you get? 1. Sine of pi halves 1. Cosine pi halves? 0. So you're down here. So this will go in that direction. So there are multiple ways to do this. All right. Okay, so that's the idea about parameterization. Now we want to switch over and talk about the idea of tangent lines. It says, hey, suppose I have a parameterized curve. So here's a parameterized curve. And I say, I want to know what's happening in this neighborhood. Well, no problem. We say, just zoom in. So we zoom in on that neighborhood, and we say, aha, locally, it looks like that, roughly speaking. Say, all right, but what if I zoom in again? Say, all right, again, no problem. And then when you zoom in again, you say, locally, it looks like that. So locally, it looks flat. We say, okay, great. We love flat things. That's all of calculus, trying to understand the world through flat things. So now we have our flat thing. We usually call it a tangent line. I say, all right, I want the tangent line. Now, how do you find the tangent line? You need two pieces of information. You need a point, and you need a slope. Well, the point comes from the parameterized curve. So that's not too bad. How do you get the slope? Well, you say, okay, what do we usually call slope? Rise over run. That's like the slope of a line. What is rise? Change in y. Run, change in x. So rise over run, change in y over change in x. And when you hear the word change, you think derivative. So change is just sort of another word for derivative. Change, rate, these all mean derivatives. So change in y, that's how fast y is changing at that time. That gets you y prime of a. Change in x, that's how fast x is changing at that time. X prime of a. So you say, y prime of a over x prime of a. So we think of this as our dy dx. And when you write it down, it says, this makes sense. Y prime of a, x prime of a, life is good. All right. Well, let's try this out. Find the tangent line to the curve t cubed minus 4t plus 5 and t to the fourth plus 3t squared minus 7t at time t equals 1. All right. So we're looking for a tangent line. So we say, no problem. We're going to find ourselves a point, and we're going to find ourselves a slope. All right, let's talk a point. How do we get our point? Plug in 1. Yes. Okay. So we plug in 1. So at time t equals 1, we'll get 1 minus 4 plus 5. 1 is a very nice number. To plug in 1 plus 3 minus 7. 1 minus 4 plus 5, also known as 2. 1 plus 3 minus 7, also known as negative 3. All right, we have a point. We're halfway. All right, how do we get our slope? Yeah, we use what we just wrote down. We want y prime of a over x prime of a. Derivatives are going to be involved. It's almost impossible to talk about finding a slope of a tangent line without there being a derivative at some point. All right, now here's where I often make mistakes. So oftentimes we have an x of t and a y of t. So x of t, I'll show you the mistake I make a lot. T cubed minus 4t plus 5. So what is x prime of t?
3t squared minus 4t.
3t squared minus 4. Y of t is t to the 4th plus 3t squared minus 7t. So y prime of t is 4t cubed plus 6t minus 7. Good. Good. Now you're like, that doesn't seem like you've made any mistakes. No. Here's where I make my mistake. Because I often think of x and y, and I say, oh, take 3t squared minus 4 or 4t cubed plus 6t minus 7. But no, don't do that. What should be on the top? The y stuff. So, okay, so really when we're looking at dy dx, it'll be 4t cubed plus 6t minus 7 divided by 3t squared minus 4. All right. Now, is that our slope? And why not?
That's just the equation.
It's the equation for slope at any given time t. We're after a number. How do we turn this into a number? Plug in t. And in our case, we know what t to plug in. We're plugging in time t equals 1. So evaluate at time t equals 1. And this gives us that our slope is, well, 4 plus 6 minus 7 divided by 3 minus 4. 4 plus 6 minus 7, also known as 3. 3 minus 4, negative 1. Put them together, you get negative 3. Now we have a point, we have a slope. We put them together, we get a line. Okay, so we'll just do our y minus our y value is equal to our m x minus our x value. So y minus y naught equals m x minus x naught. And since they didn't tell us that we have to simplify, that's a great answer. All right. Well, a couple of comments. There are some tangent lines that we tend to be thinking are very interesting tangent lines. Okay, so what happens if y prime of a is 0 and x prime of a is not 0? What kind of tangent line do you have there?
Flat.
It's flat. So this is a horizontal tangent line. So if a problem says, hey, find all the horizontal tangent lines, it says, oh, find where y prime is 0. But what if you said, x prime of a was 0, but y prime of a was not 0? What would that correspond to? It says your y value is changing, but your x value is not. So you're moving literally up and down. So that's vertical tangent lines. So if you're looking for vertical tangent lines, that says, hey, you really set the x prime term equal to 0. What if x prime of a is 0 and y prime of a is 0? Then what? What does that mean? Zero over zero means more work. More work. Yeah. You're not able to make any conclusion. Oftentimes when that happens, there's a cusp coming into play. But that's a story for a different time. Okay, so that's first derivative. And as any good hobbit would say, we've had one derivative, yes, but what about second derivative? Okay, so let's talk about second derivative. Now, before we actually put down what it is, intuition, you're like, oh, I want the second derivative. You're probably thinking y double prime of a over x double prime of a. And that would be nice, but not right. So, let's go ahead and say what does happen. To find the second derivative, and second derivative gives us information about the curve, it gives us concavity. What do we do? Well, we have notation for second derivative, d2y over dx2, right? d squared y dx squared. What that's short for is we're asking the question, how is the derivative changing as we change x? That's what we're asking. As we change x, how is the derivative changing? Well, when we take a derivative, we say, what's going on here? We're saying, what's the change in this term on the inside? What's the change in dy dx compared to the change of this piece, the change in x? All right, so it's change in dy dx over change in x. But then we apply our rule. When we see the word change, we think derivative. So if I want to take a change in dy dx, I'm taking the derivative of dy dx, which we know is y prime over x prime. And then downstairs, the change in x is the derivative of x. If you do the quotient rule and add in this extra term downstairs, you get to the equation x prime of t, y double prime of t, minus x double prime of t, y prime of t, over x prime of t cubed. Now, you're probably thinking, do I have to memorize that one? No. Memorize this one. This is the easier one to remember. So if a problem says, hey, I need you to find the second derivative, you say, I know what second derivative means. How is the derivative changing with, how is x changing? And then you write down, here's what it means to see what the derivative is doing when it changes. Here's what it means to say what x is changing. Okay, so here we have a question. Find the second derivative of t cubed minus 4t plus 5 over t to the fourth plus 3t squared minus 7t at time t equals 1. This might sound familiar. Have we seen it before?
Yes.
Yes, we have. It's the same problem, except now we're after second derivative. Okay, so we can save ourselves some work because we wrote down the first derivative. So we already know that dy dx, that's 4t cubed plus 6t minus 7 over 3t squared minus 4. And we can say, all right, now we'll just apply our basic philosophy. And we say, what do we need? Well, we need to take the derivative of 4t cubed plus 6t minus 7 over 3t squared minus 4 over the derivative of just x. Well, we can read what x is. It's right upstairs. T cubed minus 4t plus 5. All right, good. Just when you thought you could forget about the quotient rule, it pulls you back in. Okay, so you're probably saying, I'll just look it up on the formula sheet, except it's not there. I know. They expect us to know stuff? Crazy, I know. Okay, so what's the quotient rule? A lot of people like to remember it as low, d high, minus high, d low over the bottom term squared, low squared. All of that is over 3t squared minus 4. Okay, so if we were to write this out, this would say 3t squared minus 4, 12t squared plus 6, minus 4t cubed plus 6t minus 7 times 6t, divide by 3t squared minus 4 cubed. Now, should we expand or should we plug in? Because we have to do both, right? At some point we have to simplify, and at some point we have to plug in. What should we do first, and why? Plug in! Correct! Why? Because we love ourselves, and we want to give ourselves the best opportunity to succeed. And it's so much easier to simplify numbers than to simplify algebra. Okay, so now we plug in at time 1, and we get the following. 3 minus 4 is negative 1. 12 plus 6, 18. Minus 4 plus 6 4 plus 6 minus 7 is 3 times 6. 3 minus 4 is negative 1. Negative 1 cubed will be negative 1. All right, so we have minus 18, minus 36, divided by negative 1, leaves us with a positive 36. And at this point, that's all it asks us to do, is say just find it. Now, we could give an interpretation. What is this telling us about the curve? It's concave up. So that's giving us information about the local behavior of the curve, but for right now, we just need a number. All right, any questions? Good. Then on to applications. So, we're going to start by talking about length, and there's not really much of a surprise here, but I do want to make a comment. So when we talk about parametric curves and length, there is a bit of a subtlety. We write down length equals, but we aren't actually computing length. We're computing something slightly different. What we're actually computing is distance traveled. And so I want to make clear about that distinction. So let's do a quick jump back to this slide right here and talk about item E. So I can ask a question, what's the length of this curve? Is that the same as doing the distance traveled? Well, what happens here is we saw that the particle went back and forth twice. And so, in other words, it really is twice the length of this curve in terms of how the particle travels. So if you think of parametric curves as saying, hey, how is this particle moving around? That's what we're actually computing. Now, in practice, we're never going to have to get into that subtlety, but I don't want to lie to you because I want you to understand how these things work. Okay, so we're finding how far the particle has moved along the curve. And we have a parametric curve, x of t, y of t. We start at A, we end at B. And we start thinking to ourselves, well, what should we do? Well, since we're taking calculus, and we say, well, we've got this tool, integration. And we always do the same thing. We take our curve, and we're just going to cut it up into parts. So here's this curve, that's parametric, and we cut it up into pieces. Now, what's happening here, of course, is we're not necessarily cutting up the curve in some way that makes sense to us. We're cutting up our curve in terms of time. And so there's sort of this philosophy that comes into play. How can we think about parametric curves? Now, one way to think about parametric curves is we could say, I'm here at time t equals A, and over here I'm at time t equals b. So you might say, so what we really did is we took the interval a to b, and then we somehow mapped it onto the curve. And that's, in spirit, is what's happening. But there is a little bit of a subtlety in that there can be dilation. So some parts of the curve you might travel quickly, Some parts you might travel slowly. So, okay, but we're breaking up time, which breaks up our curve. And now we say, okay, instead of measuring this, we'll just think about there being as straight line segments between points that we travel. Now, it won't be precise, because it will do pretty poorly whenever we have turns, but it won't be a bad estimate. How do we get better estimates? Smaller pieces. So we do lots of small pieces, we add them up. And adding stuff up means to integrate. So I say, okay, what's the length of a small part? Well, I take a small part, so here's my small part, and I think of it as there's a triangle. There was a change in x that happened, a change in y that happened, and then there was a piece of the length that happened. And because it's straight line, I can think of it as a right triangle, not the wrong kind, the right kind. Pythagorean theorem says that the length here satisfies delta x squared plus delta y squared equals that length squared. So the square root of change in x squared plus change in y squared. Now we can make that more precise. We say, well, I can think of it as change in x over change in time. I can add some delta t's in, but if I add some delta t's in, I also need to make sure I balance it. So net, if you look at your delta t's, the delta t's all cancel. And now I say, well, change in x over change in time, that means the derivative, x prime. Change in y over change in time, that's y prime. And then, of course, your piece of t. So a little segment of the curve is your x prime squared plus y prime squared dt. So this is the length of a little piece. Now, what do? We add all the little pieces up. And that is done by integrating. So integral from a to b, square root x prime squared plus y prime squared dt. And you'll see this is our second time we've talked about length. We are going to do one more length measurement before the exam. So here, this is a scenario, length of parametric curves. All right. Well, let's try it out. Any questions? It should feel familiar. We still, of course, have our challenge, the square root. Square roots are hard. So you have to be careful. And whenever you deal with square roots, sort of what's the underlying plan? The underlying plan is, let's try to get something on the inside that's a square, if we can, or maybe there's some kind of smart substitution, but look for squares first. So find the length of the parametric curve, and then we have 7/3 t cubed plus t, 2/3 2t squared plus a quarter to the 3/2. And we're going from 0 up to 2. So as we look at this problem, there's a couple of clues that we see here. You know, we're learning to read these problems. Things like length and parametric are big clues that we're going to do length of a parametric curve. So that helps us get to the right formula. Now, even if it hadn't said parametric, how would we know that this is parametric? You see t's. When you see t's, it's like, parametric. All right, good. Well, we just say, great, we know the formula, the length, integral a to b, well, in our case, 0 to 2, and square root of our x prime. So what's the derivative here? Seven t squared plus 1 plus, and then we're squaring that. All right, so we have, we'll write this down for reference, a to b square root x prime of t squared plus y prime of t squared dt. Don't forget your squares there. Okay, so this derivative is probably going to be a little bit longer, but let's just take it turn by turn. We have the 2/3. We apply our chain rule. What happens to our 3/2? 3/2 will come down. Oh, so that's probably why they put a 2/3. Then we still have the same thing on the inside, but what's the new power? 1/2. Cool. Are we done taking that derivative? What's left? Chain rule. Okay. Derivative of 2t squared plus 1/4. 4t. And all of that's squared. Now, the vast majority of work in these problems is going to occur in working on simplifying. So this part right here, simplifying, this is the key part. So make sure you don't rush it. All right, but we're short on time, so we're going to rush it. Okay, but that's okay. I think you'll trust me when I say this is 49 t to the 4th plus 14 t squared plus 1 in the first term. A plus b squared. A squared plus 2ab plus b squared. The 2/3 and 3/2 cancel. If you have something to the 1/2 and you square it, well, that just becomes something to the 1. So 2t squared plus 1/4. And 4t squared, 16t squared. Okay, don't worry, more algebra still to come. Just when you thought, there's no more algebra, we'll keep it coming. 2t squared times 16t squared, 32t squared. 1/4 times 16t squared, it's t to the 4th. 1/4 times 16t squared, 4t squared. 49 plus 32, 81. Now, 81 should sound nice, because what's true about 81? It's a square number, it's 9 squared. 14 plus 4, 16t squared, and 1. Oh, yeah, 14 plus 4 is 18. See, that's why you shouldn't race. Now, you're thinking that this should be a square. So in the back of your mind, you're like, you're thinking, this is a plus b squared. Well, if it was, you'd need this to be a squared. Just go in your powers. It would have to look like a squared, 2ab, b squared. So what would a need to be for this to work? 9t squared. What would b have to be for this to work? 1. And that should be true. Now, you should double check, does it actually work? If it doesn't, you should check your algebra, because you should get something nice if they're asking you to compute. But okay, at this point we've done a lot of work to get a square on the inside, which means we're ready to just take the square root, 9t squared plus 1, because the square root and the square cancel. Integral of 9t squared, 3t cubed. Integral of 1, t. Plug in 0 to 2. When you plug in 0, you get 0. And then you get 3 times 8 plus 2, which is 26.
I trust you.
And that is the right answer. So